go ahead and get started here today. Guys, just want to first of all welcome you that this is a unique year, and I want to make sure that we're clear on some things before we get started on our first lesson here. So for those of you that are remote learners, here is how things are going to work for you. You guys already have a Canvas set up for you. And in your integrated 2D right here, you'll notice that when you click on that tile, you should have a link that says Mr. Parsons page right here. And when you click on that, it's going to take you to this. Here's where you want to be. Since we're integrated math 2D, you're going to want to go ahead and click over here on this tab over here. It says integrated math 2D. Now if you notice right here, this is going to be the lesson for Friday. And for Friday right here, there's going to be a link in each of these days when we do a lesson. So in this link right here where it says lesson 1.1 notes, you'll probably want to pop that open. And it should take you to exactly what I have in front of me. So if you want to print that and then write on your own note sheet, that's fine. Or I can print stuff here at school and you can stop in and pick that stuff up ahead of time. Totally up to you. But we'll make sure that those resources are available in a PDF file for you to have those. So the first thing you're probably going to want to do is access that note page through your integrated 2D and Google Sites, and be ready to follow along. So once you've had time to access that, I'm going to take you over to our notes here and we'll get started here. So integrated 2D section 1.1 is titled absolute value functions, and the question we're trying to answer today is, how do the values of A, H, and K affect the graph of the absolute value function of g of x equals A times x minus H plus K? And I think the key thing to remember here is this. Anytime you're dealing with a value A, H, and K, A, H, and K are all going to be some number. Okay, and we'll explore some of this when we get through the vocabulary. But this is going to be the general form for any absolute value equation. Okay? So in order to answer our question, how do the values of A, H, and K affect the graph of absolute value functions in the form g of x equals A times the absolute value of x minus H plus K, we need to first of all be able to translate graphs of absolute value functions. Translate simply means sliding them left or right or up and down. Okay? We'll talk about stretching and shrinking and reflecting graphs of absolute value. And then we're going to take some of the translations and some of the other transformations in goal number 2 here and put them together and see what it looks like to combine transformations of graphs of absolute value functions. So with that said, we need to get some vocabulary established and make sure we understand this. So the first thing we have is absolute value function. And an absolute value function is something that contains an absolute value expression. So absolute values are expressed by a bar. So we might have something like y equals absolute value of x minus 6. Okay? The bars are what give it the function of an absolute value function. Okay? Over here on the right, we have a function f of x equal to absolute value of x, and this is considered the most general absolute value function there is. When we have the most general absolute value function there is, we call this the parent function. Okay. Now you'll notice that with the absolute value of x, it forms a V shape. Okay. When I input 1, the absolute value of 1 is 1. So therefore the point 1 comma 1. Okay. If I would input negative 1, okay, when I input negative 1, the absolute value of negative 1 would be positive 1. Therefore the point negative 1 comma 1. Okay. And you could plug points in and you would see that it forms that shape. Okay. Down here, the lowest point, 0, comma 0, you have a V shape from an absolute value function is called the vertex. The vertex is simply the highest or the lowest point of an absolute value function. For our purposes today, in this example up above, you need to understand that above the point 0, comma 0 is the vertex. 0, comma 0 is the vertex above. Okay? You're going to hear us discuss a lot about vertex form up here. Vertex form is simply that long function where an absolute value function written of the form f of x equals a times absolute value x minus h plus k, where a cannot equal 0. If a equals 0, everything would be flat and you wouldn't have a V shape. Okay? Again, the key idea here is this: a, h, and k are all values or parameters that move the parent function. And we'll talk about that more here in a bit. But a, h, and k are values that are going to move the parent function. Okay, two things that kids struggle with a lot. We'll want to make sure we get this down because it's not going to go away this year. Domain and range. Okay? The domain, here's what I tell kids all the time. The domain is like the x value of the function. What x values are being graphed? The range is like the y values that are being covered in a graph. The way I remember this is in the dictionary, domain would come before range just as x comes before y in the alphabet. And again, the domain is going to be the set of all inputs, or the x values covered by a function. If you can think of domain as working left to right. Above, if I would look at the graph of my parent function, I would say, well, if I look at this graph from left to right, I would say this graph is continuing to widen out in both directions. So I would say all values of x down here are covered. Okay? It goes infinitely to the right and infinitely to the left. So above, I say the domain, which I use a capital D for, is all real numbers. It includes every single value of x because that graph goes on forever. It continuously goes to the right, continuously goes to the left. And then for your range down here, you notice you have a lowest point. Okay, if you think of the range as moving from what values of y does my graph cover? My range has an absolute lowest point, and that lowest point again is at 0, 0, but the range is going to cover the y values and everything above. So I'm going to say, well, my range is in the above function, or that parent function if you will. The range, which I use a capital R for, is going to be all y values that are greater than or equal to 0. Okay? Again, it has a lowest point at 0. And the graph covers everything above that. So therefore your range would be y greater than or equal to 0. Now I have to admit, teaching to a room of no students is kind of weird. So I would encourage you guys, as you're watching lessons, pause, get stuff down if necessary, and then continue to move on, because I'm not going to take very many pauses here as I teach to a classroom with no students in there. Kind of like watching my sports lately. Teams are playing, but no one's in the stands. Weird. All right, so let's take what we kind of know already and apply it to example 1 here. Example 1 says, what happens when you graph g of x equal the absolute value of x plus k and g of x equals the absolute value of x minus h? If you notice to this parent function right here, we're doing something on the outside of it. We're adding some constant k. And then for this function g of x here, if you notice right here, we're going to subtract within the graph right here. So what I've done here, guys, I've set up a little introduction here in Desmos, and Desmos is one of the calculators that we will use often. And I've just got to make sure I've got the right thing here. I've set up the general form up here by this, and what I've got up there is the vertex form of an absolute value function. And that vertex form of the form y equals a times x minus h plus k is set up with what we call sliders. If you notice down here in part 2, I've set the a value to equal 1. I've set h to equal 0. And I've set k to equal 0. So what this really becomes is 1 times x minus 0 plus 0. Most generally, kind of like what you saw on your notes in the top page there, your parent function is a absolute value function where your vertex is at the point 0, 0. I'm going to take a second here. I need to do something with my monitor here to try and make this a little more appealing to you. So give me 1 second here. I can't see my vertical lines. That's better. That's better. Okay, so let's talk about what happens here. I'm going to work on this part right here. I'm going to work on what happens when we slide A around, if you will. Okay? So if you notice right here, A is 1. When I move A up to be a certain value, my graph kind of gets steeper. If you notice right here, I'll go up to about 4. Okay? And what you can kind of notice is I go from this point, 0, 0, my slope, which was rise 1, run 1 before, now is actually rising up here 4. And we'll get this here set the best I can. I went from a slope of 1 to a slope of 4. Okay, I rise 4 for every 1 unit I run. When A was 1, you notice that I went from 0, 0 to this point up here, maybe 1, 1. Okay, so that A value is going to have some change in your slope. And we'll look at more of this right here. Another one that we're going to look at is what happens when we change the H value inside the absolute value brackets. Okay, if I make H a positive value, so it becomes like H equals 4, it would be like X minus 4 in there. Subtracting 4 is like moving everything to the right 4 units. So then, if I have a negative value in here, like say negative 6, you can see the graph transform to the left 6 units. Okay, we'll go back to 0 here to where our parent function was, and we'll look at the effects of K. If I change the K value on this, if I make K a positive, the graph simply translates up. And if I make K a negative value, it simply translates down. So what we want to do is I'm going to get rid of some of these here. And we're going to use decimals here to talk about.
Mr. Denner, can you come to the office, please? Mr. Denner, please come to the office.
Students not here and still get interrupted. All right. So let's go back to this example 1 right here. It says compare each of the graphs f of x equal absolute value of x to the following and describe the domain and range. Okay. Well, I think it's important to use decimals. Right here, if you notice, we have the absolute value of x in this one plus 2. That would be like this plus k value right here that moves stuff up and down. Okay. So what I'd like to do here, kids, is this. I think it's important to remember that your parent function is this right here. F of x equal the absolute value of x for all absolute value functions is your parent function. And I've got to be honest with you, decimals is going to be a powerful tool for you guys to use all year long. And I think what I'm going to do here is I'm going to jump into decimals and I'm going to go in here and I'm going to type in that y is equal to, and then over here you have this functions bar. Click on that. Let's see, it might be under miscellaneous stuff here. And under miscellaneous stuff, actually, no. Stats, trig, no. Oh, there's the absolute value bar over here on the left. You're going to type that in, absolute value of x. I'm going to graph that. That's your parent function. Now, in that next example, example 1, that first part of there, we have the absolute value of x plus 2. Okay, based on what we saw with the sliders, adding something outside of the absolute value bars is going to simply translate that up. So let's just confirm that here. If I go in here to a second tab, I go y equals absolute value of x, and you got to be careful on this. Make sure you get outside the absolute value bar over there and go plus 2. That's what's graphed. So if you notice, my parent function here in black, vertex was at 0, 0, and now my vertex has moved up from the translation 2 units. Okay? So, guys, what I'm really getting at is this. Kind of look at that vertex for all parent functions and say, well, where did it go? Okay. Okay, and once you've got that established, you kind of decide, all right, well, I know how to describe that movement. I think from that movement, then I can define a domain and a range. Okay, so let's go back to this. Okay, describe the transformation, describe the domain and range. Okay, this plus 2 out here took the parent function and shifted it up 2 units. Okay, now the domain and the range, I've got news for you about domain for all absolute value functions. What values do they cover, left to right? Well, all absolute value functions are going to move to the right and to the left completely. So the domain for any absolute function will always, always, always be all real numbers. Okay? The domain for any absolute value function will always be all real numbers. The range is what gets tricky, but you have decimals to help you with that. And in decimals, you can see that on this red function, the one that we transformed from the parent function, you can see that the absolute lowest point is at 2. So I say to myself, well, are all the other points that are graphed on that above 2 or below 2? And in this case, definitely above 2. So what I'm going to choose to do here is say, well, my range then is all y values greater than or equal to 2. So over on the right, we have the function m of x equals the absolute value of x plus 3. And again, we want to compare it to our parent function. F of x equals absolute value of x. And we want to see what happens. So I'm going to jump back in here. I'm going to get rid of this right here. And in this one, we've got an absolute value of x minus 3 in here. Now, if you notice, this time, parent function, vertex was at 0, 0. Now the vertex is at 3, 0. Anytime you have transformations that translate stuff to the right or to the left, I always tell kids to kind of think opposite of what you see. Inside of here, you kind of see a minus 3, but that actually took our vertex and moved it right 3 units. So if you see a minus sign in there, typically that means it moved to the right 3. Minus might then go to the left, but that's not true. So if there was a plus sign in there, it would actually move to the left. So here's the point. Once I've established and say, well, everything just moved to the right 3 units, okay, I'm going to describe that movement. And now we have to identify our domain and range. Anybody remember what I said about all domains of an of an absolute value function? You got it. All real numbers, because it goes all the way to the left and all the way right. It just continues to widen out as you move up. So it's all reals. So the real question becomes, for my range, what y values are covered? And if I look at the graph again, I can see here that, well, my lowest point at the vertex is 0, and we're covering everything above 0. So for my range, I would have all y values equal to or greater than 0. So I express that as all y values greater than or equal to 0. Okay? Now I think for you kids that are online learning right now and hearing this stuff from me, I think it's a good idea to make sure you have everything down after each page. So you might want to pause here, check, make sure you've got everything. Just quick review, make sure you understand everything that's there. If not, go back, watch what may not have made sense, or email me. We can meet through Google as well to talk about this, but make sure you have stuff down. Again, things may not make sense right at the beginning, but let it progress all the way through. I think as we continue to move through stuff, you'll find out that, oh, that's what he meant by that earlier. Okay? So let's go ahead and take a look at page 2 here. And on page 2, there's some important information. Anytime I highlight stuff in yellow, if you'll notice on page 2, anything highlighted in yellow, that's going to be pretty important stuff. It's called a core concept. You want to make sure you refer to that and understand what's there. Okay? All right, so example 2. In example 1, we were simply looking at moving stuff left and right. Now if you notice right here in example 2, they're saying, ooh, what happens when we start messing with that A value? Okay. Now this is the one that if there is a tricky part, maybe this is it. And here's what you're going to choose to look at. I'm going to get rid of that. Here's my parent function. Again, kids, slope. Remember, slope, you should remember, is a rise over run. So in this case right here, I have just the function f of x, or in this case y equals x, absolute value of x. There's no number out front, so we assume or imply that it's 1. So in this case, as I move up 1 and over 1 all the time, that's kind of the slope of each side, okay? And it mirrors itself. And then this will go up 1 and back 1, up 1 and back 1 to the left, okay? Up 1, over 2, or up 2, over 2 is a slope of 1. Now, I want to go back to this slider stuff. I'm going to put an A out in front of here. What happens when I put an A out in front here with a slider? Okay, if I make this A value bigger than 1, my slope from the right side and the left side gets steeper. Okay, in this case, my slope on the left and the right is 4 and negative 4 respectively. Okay, now if I make that something smaller than 1 but greater than 0, say maybe 1/2, you can notice right here that the vertex from 0, 0 goes up 1 and over 2. Rise 1, run 2. That's a fraction 1/2. Okay? What happens when we start looking at negative A values? There's something pretty unique that happens here. By the way, we never want A to equal 0, because when A is 0 right there, we lose our V shape. Okay? But when I start going this way, that V shape, when I start dealing with negative values, now it becomes a mountaintop. Okay? It gets flipped over the x-axis. So anytime you have negative A values, you're no longer talking about a V shape, you're talking like a mountaintop, if you will. And the vertex is no longer a minimum, it's actually a maximum. So we'll talk about the effects of that. So, back on our notes. It says compare each graph to the parent function, f of x equals absolute value of x. You should have a pretty good understanding of what that is now. Describe the domain and the range. Okay? Well, let's just go ahead and put that 1/2 back in there. So I'm going to change that A value to a 1/2 or 0.5, okay? And I want to put my parent function back in there. Well, let's do it this way. Let's do that, and let's go and get rid of this slider, and let's type in y equals 1/2 x, 1 over 2 x. Oh, I need an absolute value. I'm really messing stuff up here. Y equals 1/2. And then we want the absolute value of x. Okay? Now, if you notice right here, our parent function here in black, and then our new function, 1/2 absolute value of x in green, we're going to say that this is a vertical shrink, meaning this. If I picked on a point like, oh, let's see, I'm going to put some points in here. One point that's on the absolute value of x is 4, 4. And there it is. All right? Now, the point directly below that, if I would draw a vertical line straight through this purple line, the point that's below it on the green graph is at the point 2, 4. And what we call this, kids, is known as a vertical shrink. Oh, I don't want to do it that. It's 4, 2. Right, 4 and down 2. Okay, the 2 points right here, the purple one and the black one, they line up. Now, again, keep in mind, the black graph is our parent function. The green one is our transformed function. Right? And so right here, kids, we call this graph a vertical shrink, meaning we're pushing all these points from the black graph closer to the x-axis. We're shrinking it down closer to the x-axis. So we say, all right, talk to me about this. This is going to be what we call a vertical shrink. Whoops, I don't want that color. We call this a vertical shrink. By a scale factor of 1/2, okay? And then again, your questions come up, what happens? Domain first, and then range. What are they? Again, told you about the domain. The domain is always going to be, for any absolute value function, all real numbers. Okay, in this graph, it continues to go all the way to the left and all the way to the right. When you're talking about range, you're asking yourself, where is the vertex? And are the points that are covered above or below that? Well, my vertex for the green graph, the transformed one, still at 0, 0. And everything's above that. So I'm going to say the range in this situation is y values greater than or equal to 0. Okay? Now this next one, r of x equals negative 2 times the absolute value of x. Nothing really difficult here. Instead of, if 1/2 is a vertical shrink, something between 0 and 1 is a shrink, then something greater than 1 is going to be a vertical stretch. It's going to pull points away from the x-axis. And I think that you'll see that over time the more experience you have with decimals. But if I go in here and I type in y equals negative 2, absolute value of x, you can see two things that have happened. Number one, instead of being a V shape, it's now a mountaintop. So it got flipped. Okay? If I would have left this just as positive 2, you can see the green graph, those points that line up on a line, the green graph stretches higher up, or steeper if you will, meaning vertical stretch. It's being pulled further away from the x-axis. But when you throw that negative in there, then it flips it over the x-axis. So what we would need to say here for some kind of a description in movement would be, first of all, it flips, and then this a value out in front is a 2. 2 is greater than 1, so it is going to be considered a vertical stretch. So same thing, they still want you to describe the domain. They want you to describe the range. If anybody misses domain at this point, I'm going to be upset. Again, it's all real numbers. But the range in this one, a little trickier. If I go back to my graph, I notice that instead of having a low point, we've got a maximum point, or a high point. And that high point happens at 0, 0, but in terms of the y values that it covers, that green graph actually lies below 0, 0. So I would say my range is now going to be all y values not greater than this time, but less than or equal to 0. So here is what I'm looking at for a range in this example. Y values all less than or equal to 0. So I think you've been able to see through decimals what this kind of looks like right here. So this kind of ties into this core concept right here. What do all of these values, A, H, and K, do for vertex form? And that's kind of the essential question we were asked when we started this. What do these values do to absolute value functions, and how can I use them to maybe describe a graph if I didn't have decimals available? Okay? So core concept says an absolute value function of the form f of x equal a times the absolute value x minus h plus k has the following properties. Your vertex will always be at the point h comma k. All right? So if I had this as an example, if f of x was equal to 3 times x plus 6 minus 2, now notice here, guys, this minus sign's tricky. I have a sign down here that says plus. H is not 6. H would actually be negative 6, because I could write this as the absolute value of x minus negative 6. That double positive, or that double negative thing making a positive would work. Okay? So the vertex in this case would be at the point negative 6 comma negative 2. And then they talk about lines of symmetry. The line of symmetry will always be at the point x equals h. In this case, x equal negative 6. I should probably go talk about that in a graph here. Line of symmetry just takes an absolute value function and divides it into 2 equal parts on the left and the right. So in this case, right here, if I would go ahead and punch in x equals 0 here, anytime you have this, x equals 0, that red line cuts those absolute value functions in half left to right. So they're going to ask you about that. All vertical lines cross the x-axis. They will always start out x equals some number. And in this core concept, it turns out that your line of symmetry is going to be about the line x equals h. All right, let's continue here. Example 3. We're making some good progress right now.
we just did the online order of Saget.
Okay.
You should get an email, but it'll have the invoice. Could you forward that to me?
Sure will. Thanks, Kim.
And it maybe got changed. We're not sure.
Okay, I'll look into it here and I'll let you know. Is that okay?
Perfect.
All right, thanks a lot. I appreciate it. Okay, let's go ahead and do what they're implying here in example 3. We're going to graph the functions f of x equal absolute value of x minus h plus k, and g of x equals f of ax. Okay? So we want to graph the two functions. So let me get into decimals and do this. The first one is the absolute value of x minus 3. That minus 3 is going to take the parent function and move it right 3 and up 1 with the plus 1. So we're going to use decimals for this and compare the graphs and see what happens. Okay, so let's go. Clean these up. All right. So my first one, I need to look at this, was the absolute value of x minus 3. There's that right 3 movement from 0, 0. And then outside of it, always make sure you get outside if you have to. Get outside the absolute value bars. There's the first one. Okay. And I want to take note of our vertex here. Our vertex turns out to be the point right 3 and up 1. That's that h comma k value. Now this one's a little trickier. This next one that we're going to graph, all of a sudden, instead of having just x inside the absolute value bars, we now have a 3x in there. Okay? No worries. I'm going to show you a shortcut. So we've got the absolute value of, in this case, 3x minus 3 plus 1. Okay? Now, a couple things are happening here. Your vertex moves from 3, 1 to 1, 1. Okay? And something I want to keep in mind and show you this is kind of tricky. All right? This would be considered a horizontal shrink right here. This point that's here at 3, 1 gets closer to the y-axis. So I'm moving left to right, moving that vertex left to right. This would be considered a horizontal shrink. We're compressing everything up there. So this is now only 1 unit away from the y-axis. Okay? The y-axis simply being the equation x equals 0 here. Okay, if you notice this point 3 comma 0, this point 3 comma 0, or I'm sorry, 3 comma 1, now it becomes 1 comma 1. Okay? It compressed itself. It's a horizontal shrink right here. All right? So it got closer to the y-axis. If that vertex would move further away, then we would consider that to be a horizontal stretch. But since that point from the one that was original in blue to the one in green got closer to the y-axis, we would consider that to be a horizontal shrink. Okay? So it says compare them. Okay? They look much the same. You have the x minus 3 component, you have the plus 1. Here's the x minus 3 component, the plus 1. Only difference is you have a value in front of x inside the absolute value. Okay? If that value is going to be inside there, which is more than 1, you're going to have a horizontal shrink. Okay? So what happened here from these two is that we have a horizontal shrink. And what does that mean? Well, it means the points from the original get closer to the y-axis. It means the points from the original graph, in our case, f of x, absolute value of x minus 3 plus 1, had a horizontal shrink. It meant that when I put 3 in front of the x here, those points moved closer to the y-axis. All right, kind of a tricky concept there, but I think in time you'll have a lot of practice with this, whether it's absolute value functions, quadratics when we get there. lots of functions that this applies to. So the more you understand in this section, that's going to carry over to other types of functions moving ahead. So pretty important stuff here. All right, so again, make sure this page you've got everything down. Kind of review it quick before we move on to the third one. And this third one, going to kind of give you a cheat sheet here, okay? Up top in example 4, it says graphing g of x equals a times x minus h plus k. Again, the essential question, what do a, h, and k do to our parent function of the absolute value? Well, I've got some rules, I think, to make this easier, okay? This says the following. If a is positive, it changes slope. If a is a positive, it changes its slope. Okay? If a is positive, you're still in a V shape like that. Okay? Now, if a is greater than 1, still the slope will be steeper. And if a is between 0 and 1, it's going to flatten out a little bit. So like a slope of 1/3 means you're only going up 1 unit for every 3 you go over. Okay? A is negative. Well, same thing for this, but if A is negative, instead of having a V shape, you're going to have a mountaintop. Okay, so the A is negative, it flips over the x-axis. What about the H? H is simply going to move it left or right. Okay? If you have something in here like minus H, then you're going to move right H units. And if inside of there it says plus H, you're going to move left H units. Okay? And then K is going to move stuff up and down. K is the part outside of the absolute value on the end. So if you have a plus K, like plus 6, you're going to shift your vertex up K units. And if you have a minus K, you're going to shift stuff down K units. So quite honestly, kids, this last example, let's see if what we've learned ties into what we need to know here. Okay? Here's a great example. Let g of x equal negative absolute value of x plus 1 plus 2. Now I'm going to cheat this a bit. I don't like this negative out front here because there's no number out front. So I'm going to write this as g of x equals negative 1 times the absolute value of x plus 1 plus 2. Okay? And I think it's important to identify your a value, your h value, and your k value. Okay? This a value is negative 1. H will be negative 1 in here. Again, inside the stuff like that, you kind of do the opposite. And then k out here is a plus 2. So what I'm going to do here, kids, is this. I'm going to go ahead and draw my original function. Absolute value of x. It's just a V shape that goes diagonally here through 0, 0. I'm going to blow this up here quick. Through 0, 0 kind of goes like this. And again, the slope on this is 1. Rise 1, run 1, because there's no number out in front of the absolute value function. Now, what I know is this about the information I have here with h and k. I know h is negative 1 and k is up 2. So this is like going left 1 and up 2. So I'm going to take my original vertex, which is right here, 0, 0. I'm going to go left 1 and up 2, and I'm going to say, all right, there it is. Now, I know this a value is like my slope, but instead of making that slope of negative 1 make a V shape, I'm going to have that make a slope that is actually a mountaintop. So from that point, I'm going to go down 1 and over 1 everywhere. So this is going to kind of go down 1 over 1, down 1 over 1, and I'm going to continue the pattern until I get to the end of the graph. And same thing over here. down one over one until I get to the end, and I'm not doing a very good job sketching because I'm not calibrated the best. I'll get on track here. Come on, Parson. There we go. Now, again, part of your assignment and big ideas will be graphing stuff like this, making sure it's right, but I would always encourage you not to use Desmos to get answers, but use Desmos to take what you've done and confirm it. I would always encourage you, try it first. If you get it wrong, then look at Desmos and see. But try it first, get it right, use Desmos to confirm what you're doing. I think that's a great way to validate your learning. Let's see if we're right. So here's our parent function again. Parent function, absolute value of x. There it is. We had that graphed correct. Parent function is pretty easy. Start 0, 0, slope 1, going above. Then we had y for the function we were trying to graph on our own, equals a negative out in front, which I said call negative 1. Absolute value of x, I think we said plus 1 out there, and then a plus 2 in there. By golly, that vertex is left 1 and up 2, and it looks like our slope to this point is down 1 over 1. I'd say we nailed it. I do need to make sure I had the right stuff in there, and I think I did. Yep, we're good. All good. Okay, kids. Again, this is certainly trying times, certainly weird times we're navigating by me teaching to a class where nobody's in here to try and stay ahead. One thing I want to reiterate to you guys is if you have questions, make sure you ask, okay? Since there are no kids in the classroom, I will be moving through these kind of quickly, so I strongly encourage you to email me or get in a Google Meet with me about stuff. Be checking the site. This will get uploaded today to Friday, so if you want to start your work today to have Friday stuff done, I'm okay with that. Again, I think everything in Canvas is self-explanatory to you. I think everything that links Google Sites to Canvas for the stuff that you need to be doing is self-explanatory, but if there are issues, please let me know, because this, again, is a new experience for me to try and send out work to kids that are both in and out of school. So don't hesitate to communicate with me. All right, so you're my first COVID class I ever taught. Give yourself a pat on the back if you're still with me, and hang in there. We'll enjoy the ride together.